So today I'll be talking about a language that we are developing for neuro-symbolic programming. And this is joint work with PhD students, Ziyang and Jiani, and a research associate, Nilay, who recently got his bachelor's from UC Berkeley, the EECS department. Okay, so we are all familiar with the two predominant paradigms of programming today. One is classical algorithms, and the other is deep learning. Some have called this software 1.0 and 2.0 respectively. So classical algorithms, as we know, are suited to solve exactly defined tasks, such as sorting a list of numbers or finding a shortest path in a directed graph and so on. Deep learning, on the other hand, is suited for tasks that cannot be done adequately using classical algorithms. And there are many reasons why that might be. It may be that the tasks themselves are ambiguous, or it may be that classical algorithms are intractable, and so on. And I've just listed two of the most common examples, one being from vision, so detecting objects in an image, and the other being from natural language processing, which is semantic parsing. Okay. However, modern AI applications seem to need the complementary capabilities of both of these paradigms. And I'm going to show you three such applications, but there are many others out there. So the first is from 2017. This is a diagnostic data set that was developed at Stanford called CLEVR. Stands for Compositional Language and Elementary Visual Reasoning, where you're given an image and a natural language question. And the goal is to answer the question with respect to the image. So in this case, whether there are an equal number of large things and metal cubes. Going forward, we increasingly see video data out there, especially in this year. And here's another synthetic benchmark called MUGEN, which stands for multimodal understanding of video, audio, and text. In this case, you might be given, say, a short video clip and a piece of text. And you're asked to determine whether the text is consistent with what is happening in the video. Right. And lastly, I have picked a third application here, which is multi-agent reinforcement learning. This comes from Google Research, which developed this RL environment for one of the most popular games in the world, which is soccer. Right. Let's do a quick thought exercise and think for ourselves, what would we do to program these applications if we were to use classical algorithms and deep learning? Okay, so what you might have come up with will, I believe, at least have some overlap with what I'm presenting here. So for the first application, CLEVR, you might delegate tasks such as counting and comparison and logical operations to classical algorithms. But on the other hand, you might delegate the low-level perception tasks such as object detection or detecting spatial relationships or identifying attributes of objects to deep learning. And similarly, there are counterparts for the football benchmark that I've shown here. Okay. More generally, here is a list, by no means exhaustive, of things that I believe classical algorithms are good at and deep learning is good at. So let's go over each of these lists, starting with classical algorithms. So it is obvious that classical algorithms are good at complex reasoning. They are also interpretable. They can be executed, and they can give explanations for the solutions they produce. They're also data efficient, not data hungry. They can do compositional reasoning for various definitions of compositionality. They can even incorporate domain knowledge from experts. And finally, they can be verified. On the other hand, deep learning is great at rapid reasoning. It is also good at handling noise, ambiguity, and naturalness. It can also work with open domain. And what that means is you don't need to elaborate in great detail the vocabulary and so on that you'd like to operate on. They can even use sub-symbolic knowledge. For example, when I use the word Richard, one can associate a likely gender with the name. And finally, they can learn in context, by which I mean paradigms like few-shot learning that you are seeing increasingly in the context of large language models. Okay, so now that hopefully I've convinced you that it is worth combining these two paradigms because they have complementary benefits, let us look at some of the problems with combining them. So the very first problem that one runs into is, what is the symbolic representation one should use between the deep learning components and the classical algorithms? And how do we extract this symbolic representation from the neural components? Once we have these symbolic representations, how do we do high-level reasoning using them, right? What are the appropriate language constructs and what implications do they have? And finally, we'd like to retain the benefits of deep learning, which are efficient stochastic gradient descent algorithms, which typically struggle with discrete symbols. And so how can we extend these algorithms to make the resulting combined neuro-symbolic program end-to-end differentiable? And moreover, while continuing in the realm of being data efficient and producing a program that is generalizable. So one solution to these problems is what is called neuro-symbolic learning. So this is an emerging paradigm whose goal is to combine the benefits of both classical algorithms and deep learning by integrating them into a single system. Okay, and let me now show you visually what I mean by each of these three paradigms. So I'm going to use R to denote discrete inputs. So a classical algorithm might take an input R and produce an output Y. And you can assume that there's supervision on R and Y. For example, we might be able to synthesize this algorithm given examples of R and Y. Deep learning can not only take discrete inputs R, but they can also take unstructured inputs, which I'm going to denote by X. And furthermore, we have a parameter theta, which are the weights of the neural model. And one of the benefits of this approach is, given a lot of X's and Y's, either in a supervised setting or an RL setting and so on, we can learn the weights of the parameter theta using differentiation. And there are a lot of algorithms for computing these derivatives efficiently. Neuro-symbolic learning combines both of these paradigms, and it has these two hallmarks, which I'm going to describe using this figure. So the first is differentiable algorithms, and the second is algorithmic supervision. So what we have here is we can accept the same kinds of inputs that deep learning can accept. So this can include raw data such as images, video, audio, or even tabular structured data. And we first apply a neural model to it and obtain a symbolic representation R, which then is fed to a classical algorithm, which in turn produces the final result Y. Now, what I mean by algorithmic supervision is that we are only given supervision on the X-Y pairs, and crucially not on the intermediate result R. Okay. And secondly, what I mean by differentiable algorithms is that it is possible to differentiate this classical algorithm that you see here with respect to its input R. And so by composing the derivatives here, dy by dr and then dr by d theta, we can learn the parameter theta of the neural component without having supervision on R. Let me pause here and see if there are any questions before I proceed. Okay, please feel free to interrupt me if there are any questions. So let me now show you the landscape of methods that exist out there in neuro-symbolic learning. And I've categorized them along these two axes. So on the x-axis, we have two categories. What I call the more principled but impractical approaches, and then the practical approaches, but then those which are not easy to use and don't generalize beyond the application of interest. On the y-axis is, I again have two axes, two categories. They are the specialized solutions and the more general purpose frameworks. And so right off, we can say that something that is specialized and inefficient is uninteresting. So we don't have that. We are not going to look at that quadrant. The vast majority of neuro-symbolic learning methods fall on the bottom right, which is they are point solutions to specific applications. And it's not clear how to reuse those methods to other applications, at least not without a lot of manual effort. Yet they are very practical for those applications. On the top far left is very principled approaches such as deep prob-log that are based on differentiable probabilistic logic programming. And the reason they are impractical is because they rely, as I will show later in the talk, on an expensive procedure such as weighted model counting. Now, a good compromise between these is solutions like SATNet, which are based on numeric approximations to SAT solving. So they rely on the advances in scaling SAT solvers, yet they are not as practical nor as general as we'd like, because it takes a lot of work to port an application to the SATNet framework. Our approach, Scallop, tries to push the frontiers in both these dimensions. Okay, we want to be more practical, and we also want to be more general, right? But notice some crucial things here. Scallop is not as general as, for example, deep prob-log. Okay, and the reason for that, as I'll show later, is deep prob-log is based on a Turing complete language, which is Prolog, whereas Scallop is based on a domain-specific language called Datalog. Also note that I don't believe Scallop is the ultimate solution, which is the most practical and most general. As I said, Scallop has a domain-specific language for symbolic reasoning. And so we believe that there is a lot of room to keep going here to the corner of the top right. Okay, so how does Scallop achieve a balance between generality and practicality? So if you recall the three challenges that I showed, the first was about the symbolic representation that is used at the interface of the neural and the classical components. And our solution is to use the relational data model, which I'll go into more detail later in the talk. Our solution to the second challenge I mentioned is to use a declarative logic programming language for symbolic reasoning. Okay, and I'll again elaborate on this later. And finally, our solution to the third challenge is to support automatic and efficient differentiable reasoning to compute these partial derivatives dy by dr using a framework called Provenance Semirings. Okay, so these are the three key ideas behind Scallop, and I'll go into each of these in the rest of my talk. So let's start with the relational representation. So as you know from, say, a course on relational databases, relations are very versatile. They can represent arbitrary graphs, can even be used as a glue language for multimodal data, such as images and natural language text. They can even succinctly represent discrete probability distributions. So as I will show in the rest of my talk, answering a question like this about this image will involve actually reasoning about many words simultaneously and how to compactly represent information in all these words is something that relations are very well suited for. And finally, there are lots of practical benefits. The relational data model was proposed, I believe, in the late 1970s. It has withstood the test of time, and along with it have come various performance optimizations, such as join algorithms and efficient data structures for processing large-scale data, which we can now reuse for efficient inference and learning in Scallop. And furthermore, much of the world's structured data is locked in relational databases. And so using the relational data model allows Scallop applications to seamlessly incorporate this data as knowledge. Okay. So I said some time ago that relations are versatile. So how do we represent, say, image data and natural language data? So on the left, I've shown you a graph, which is a standard representation for images. It's called a scene graph, where the nodes can be either the objects O1 through O5, or they can be their attributes, such as their shape or the color or the material and so on. And then we have edges connecting these objects to their attributes. Likewise, natural language text can be represented using abstract syntax trees. Okay, and I've shown here one where the nodes of the abstract syntax tree are labeled A through H, and each node has a type. For example, it can be the entire scene that we are talking about, so all the objects O1 through O5, or I might want to only filter objects that have the attribute large, okay, which would in this case presumably be O4 and O5. And finally, I might want to equate the counts of two sets of objects that I'm seeing here, which is what this query is asking for, whether they are an equal number of large things and metal cubes. Okay, So in summary, we can represent a lot of different kinds of data using relations. We even have video data at this point where a video can simply be viewed as a sequence of frames where each frame has a scene graph. Okay, so now let's look a bit deeper into how, say, the scene graph is represented in Scallop. So because we are using the relational data model, every piece of information becomes a relational tuple. So for example, this tuple here says that we have a binary relation called size. What does it do? It denotes which objects have what size. So for example, we might say the object O4 here has a large size. Okay. And the way we write this in Scallop is simply using this rel keyword. We can even have types for relations. So in this case, I've created a type called expressions, EXPR, whose domain is these AST nodes from A to H. And I can say, for example, that the scene relation contains just one tuple. It's a unary relation, and it contains the tuple A. You can also add another tuple, which is D here, but I've not shown it here. Okay. Let's go a bit further. Here's another relation, which is capturing another kind of AST node, which is a binary relation called filter size. I'm sorry, it's a ternary relation. It has 3 columns. The first column is the expression ID, which is something like B. The second column talks about the child of this expression, which is A. And the third column talks about an attribute of the expression I'm looking at, which is B. And one attribute it has is large. Right? So this tuple here says that there is an AST node with ID B whose child is A, and it has an attribute large. Right? And this is a way to filter all the objects that you see in this scene that have the large attribute. Okay. We can continue this way. For example, if I'm looking at AST nodes of type count, I can define a relation in this case, which says that expression ID C is of type count, and it seeks to count the objects described by the expression ID B. Right? So this entire chain that you see here evaluates to the number of large objects in the scene, okay, which is what this question is trying to ask in its first part. In order to tell whether there's an equal number of large things and metal cubes, I first need to count the number of large things. And that is what this entire expression is doing. And this is how it's written in Scallop. So before I proceed to the next part, let me again pause and see if there are any questions. And please unmute if you have any questions at any time. Okay, I'm next going to talk about our next building block. Now that you have seen the symbolic representation that we use, how can we write high-level reasoning constructs using this symbolic representation? So our solution is to use a language based on data log. Those of you who are not familiar with data log, you must have heard about SQL, which is the most popular programming language for relational databases. All that data log does is extends SQL with recursion. It is still not Turing complete, unlike something like deep prob log. And in that sense, Scallop is not the most expressive that it could possibly be. Yet, in return for this limited expressiveness, we end up having efficient algorithms for query resolution. How do these algorithms help? Because now we can divide an application into its neural and logic components there is less work to be done for learning the parameters of the neural component, because a lot of the heavy lifting will now be done by the logic component. And if we have efficient algorithms for evaluating the logic component on different inputs, then that speeds up both inference and learning of the parameters of the neural components. Okay, so hopefully I've convinced you that in return for giving up some expressiveness, we get a lot of benefit in terms of speeding up inference and learning. Okay, and this is what crucially distinguishes Scallop from works like Deep Log. That said, the expressiveness is still quite significant. For example, many of the common reasoning patterns that neural approaches struggle with can be expressed in Scallop, and I've just listed the three most common ones here. Recursion is often needed for what is called multi-hop reasoning. We have support for aggregation, so for things like counting and so on, which again, neural networks struggle with. And lastly, negation. So we support that as well, which is yet another pattern that neural approaches typically struggle with. And lastly, notice that Datalog, just like SQL, is a declarative language. In fact, it is rule-based, and this comes with lots of benefits. For example, it is very easy to write programs in Datalog, especially as you are debugging and incrementally building a Scallop application. Rules can be verified. They can even be synthesized using ideas from inductive logic programming or program synthesis, right? So you don't even necessarily need to write down all the rules. You could even learn the rules themselves from data. And lastly, rules can be probabilistic, which allows to incorporate uncertain knowledge. Okay, so now that I've told you the high-level benefits of this language, let me walk you through some of the most common constructs in this language. So the first is, let's look at conjunction. So I told you how we express relations. For example, the fact here that the object O1 in the scene is a metallic object, right? So we use the relation material to denote what objects have what kind of material. And let us say I have another relation called shape, which is also extracted from this image, which captures what is the shape of each object, such as O1 is a cube. Once I have these relational representations, I can write a rule like this, which says, get me all the objects in the scene whose shape is a cube and whose material is metal, right? So those of you familiar with Horn clauses will understand what this rule is saying. You typically read it from right to left, okay? So we have on the left what is called the head of the rule, and on the right we have the body. And we use comma to denote conjunction. So the way to read this rule is, if O is a shape with attribute cube, and O is also has material metal, then O belongs to the relation filter object. Okay, so it's a if-then rule, also called a Horn clause. Now let's look at disjunction. What if the question was slightly changed to say, not that I want all metal cubes, but what if I wanted things that are either metallic or that are cubes? In this case, I simply write two different rules with the same head. So I filter an object O, either if its shape is a cube or its material is a metal, right? And when you evaluate this program on the relational representation corresponding to this example, then I've shown a derivation which gives you the proof why object O1 was filtered. Okay, because in this case, O1 happens to be both a metal and a cube. But if either one of these were true, that would be enough for O1 to be filtered. Okay. The last construct I'm going to illustrate in my talk is aggregation. Okay. So in this case, I changed the question again to count all the cyan cylinders in the image. So I want all the objects in the image that are of shape cylinder and color cyan, right? So in this case, first I'm going to extract all objects that match these two attributes. So they're cyan cylinders. And then I have an aggregation here since I'm trying to count them. So this syntax here says, count all objects O that satisfy this condition here of cyan cylinder. Name the count N and produce this result, a unary relation with that count. And in this case, there are two objects which are both cylindrical and of cyan color. If you squint at this image, you'll see that O2 satisfies that condition. So O2 both has color cyan and shaped cylinder. And so O2 qualifies. And so does O3 over here. It also satisfies both of these criteria. And finally, the count of such objects is 2 because by applying the second rule here, we have a derivation which explains why we have two cyan cylinders. We have many other constructs in this language that I'm not going to go into details, and we are still growing the language. I mentioned that we have recursion, and this expression here shows you, for example, how we can evaluate all the objects in the scene according to certain criteria that I described earlier. We also support negation, foreign functions that cannot be written in logic, but might need to be written in a black box language like, say, Python or Java. We also support group by and quantifiers. Let me once again pause and see if there are any questions before I proceed to the final challenge. Okay, so now I'm going to talk about the last part, which is how we support automatic and efficient differentiable reasoning in Scallop. So first of all, even though I so far showed you only discrete reasoning, in reality, all of these relations come from neural components. And so they have associated probabilities with them. For example, we don't know for certain that the object O4 is large, but we know with probability, say 0.92, that it is large, but we also believe with probability 0.08 that it is small, right? In the same way, for the natural language data, we have these 11 basic functions such as scene, filter size, count, and so on. And each of them have certain arguments like the size and the shape and the material and so on. And all of those are also probabilistic. So for example, a semantic parser might return that this AST node P is filtering objects described by AST node A and has attribute large, but only with a certain probability. And then it will have other possibilities with certain probabilities as well. I'd like to also note a nice advantage of Scallop here that we noticed in our evaluation. Even if a semantic parser, which is neural, gets a part of this parse tree incorrect, it can still recover from the mistake because it is not constructing the entire expression as a program, which many semantic parsing approaches typically do. Okay, we are instead expressing this entire piece of text as a set of relations, as a set of tuples with probabilities. And so even if we might get a part of this interpretation incorrect, we will typically be able to recover from that mistake, unlike many existing semantic parsing approaches. Okay. What we have at this point is, instead of a discrete database, we have a probabilistic database. So with each tuple that is coming from the neural components, we have an associated probability. Okay. And now we can do probabilistic reasoning over these rules that we have written. For example, we can assign Boolean variables such as F1, F2, and F3 to each of the facts that we are deriving. And we can ask, for example, what is the probability that O1 is an object that is metallic and a cube? Well, the neural network tells us that the object O1 is metallic with probability 0.91, and it tells us that O1 is a cube with probability 0.84. And since this is the rule for conjunction, we can derive that the probability of F3 is, using this formula, 0.91 times 0.84, which is 0.76. Let me do another quick example of disjunction. So here I'm showing you how to compute the probability that the object O1 is either metallic or shaped as a cube, right? And in this case, if you do the calculation, it comes to 0.99. Turns out that a general way to do these calculations is using a procedure called weighted model counting. Let me intuitively explain this procedure. So one can imagine that we no longer have a single world, okay? But every object, for example, in this image has a certain shape with a certain probability, or a certain material with a certain probability. And so one can imagine enumerating or discretizing all of these worlds and assigning a probability to each of these worlds, which is simply the product of the probabilities of the facts in that world, or their complements. So weighted model counting is this very expensive procedure for exact probabilistic reasoning. And there's been a lot of advances in making it efficient or in approximating it. But still, when we look at more sophisticated constructs or larger programs and larger databases, we quickly see a combinatorial explosion of possibilities, as I will illustrate using this final query, which is counting the number of cyan cylinders. So in this case, we have every possibility from a count of 0, in which case none of these 5 objects is a cyan cylinder, to the case where all of these objects are cyan cylinders, okay, for a count of 5. Let's just look at one of the outputs, which is the fact that there are 0 cyan cylinders in this image. And let's give the Boolean variable a name, F16. Then the probability that there are 0 cyan cylinders is simply that none of these facts none of these Boolean variables is true. What are these Boolean variables? Each of them corresponds to deriving that the corresponding object is a cyan cylinder, right? We can do that for the case of 1 cyan cylinder, and already you see an explosion in the formula here, which says that either O1 is a cyan cylinder and none of the rest are, or O2 is a cyan cylinder and none of the rest are, and so on and so forth. And in each of these cases, we get the count of 1. And as we continue this calculation, we have all 6 possibilities from 0 cyan cylinders to 5. And we can make a call to a weighted model counting solver for each of these 6 cases, and it involves an expensive probability calculation. But at this point, one has to ask, do we really want exact probabilities, right? And what about the the gradients that we wanted to also obtain. How can we get those efficiently? So as I said, WMC is exact, but quickly becomes intractable. But the key insight here is we don't need exact probabilities or gradients. Machine learning algorithms such as batched stochastic gradient descent are already approximate. But a big problem with all of these approximate learning approaches is that they have their own limitations. For example, they do not leverage logic rules, they have limited syntax, they lack generalizability, and so on. And so the key problem we set out to solve in this final challenge is how to solve these problems of probabilistic and differentiable reasoning in an approximate yet systematic fashion. And our idea is a decade-old solution for data log and deductive databases called Provenance Semirings. I'm not going to go into the math here, but let me just give you a historical perspective. So about a decade ago, there were various extensions to relational databases where researchers in that community realized that they could tag relational tuples with anything from probabilities to more complex structures such as proofs of how those tuples were derived from inputs, right? And then there was a landmark paper around, I believe, in the late 2000s, in around 2005, which showed that all of these applications of tagging relational tuples could be viewed as instances of an algebraic structure called a semiring, right? And I've shown the structure here in the table at the bottom. All you have to define is a tag space T, okay, an identity elements 0 and 1, and the operations plus and multiply. There are a few other operations such as negation, which I've omitted here. But if you can define this algebraic structure called a semiring with certain properties that a semiring has, then you can essentially get these tags computed efficiently for a language like Datalog. And that is what we have implemented in Scallop. And until now, no one had applied provenance semirings to the problem of differentiable reasoning. And by adopting Datalog as a symbolic reasoning language, we were the first to bring the benefits of provenance semirings to this new application domain of differentiable reasoning for neurosymbolic applications. I have shown you just 3 semirings here. The ones to the left are very cheap to compute because they associate with each tuple just a probability. We call these the min-max probability semiring and the add-mult probability semiring. Okay, and what these semirings do is that they are approximating the probabilistic approximation, the probabilistic computation that I showed earlier, by following the structure of the logic rules. On the far right is a semiring that we use most commonly. It is top K proofs. In fact, the weighted model counting computation that I showed you can be viewed as top infinity proofs, where we essentially keep all the derivations as we do forward chaining. Top K, on the other hand, gives you a tunable parameter K, which lets you keep only the highest probability K proofs. And let me explain this with an example here. Coming back to the example of counting the number of cyan cylinders, what we have here is a total of 10 different worlds, given these 5 objects, O1 through O5. In world 1, only O2 and O3 are cyan cylinders. And in that world, we have a probability of 0.71 according to the neural network that is either being trained or has already been trained. In world 2, objects O2 and O5 are cyan cylinders, and so on and so forth. If we did exact probabilistic reasoning, then that would correspond to the formula at the bottom right, where the K would be at least 10, because 10 is the number of worlds we have. But we could have even set K as low as 1. And if that was the case, then the weighted model counting solver would be given this much smaller formula that you see here. And in this case, we would only pick the most likely world, which has the highest probability here. Right? So I hope with this figure, you see this illustration of how you can tune how much of the logic reasoning to incorporate for computing not just the probabilities of the final result, but also the gradients, which I've not shown over here. Okay, so computing the gradients with respect to the outputs of the neural network is a straightforward extension of weighted model counting that I've not shown in this slide. Okay, so we have implemented all of this in Scallop, which is open source. We have a lot of documentation and infrastructure, and we have written a lot of different applications. And in the interest of time, I'm going to speed up a little bit here. So I'm showing just a few of the applications that are public. And we have applications from vision, from natural language processing, and video processing and multimodal data and knowledge graph querying and so on. And again, I'm going to skip some of this empirical evaluation. But we have done various experiments to show data efficiency and accuracy and generalizability and so on. So we saw that modern AI applications pose a large number of challenges, such as interpretability, data efficiency, generalizability, and so on. And neurosymbolic learning is this emerging paradigm to address these challenges. But it currently has its own problems, such as scalability. For example, it is nowhere close to crunching the amounts of data that we see deep learning approaches handle. There's also problems with efficiency, so training these programs in an end-to-end fashion. And finally, accessibility. And what I mean by that is, even though there's a large number of papers being written, there is no unified framework that can be readily used the way you can use, say, PyTorch or Python or Java, right? And so Scallop aims to address these problems by combining ideas from these three different techniques that I presented today. With that, I thank everyone for your attention, and I'll be happy to take any questions.
Thank you, Mayur, for your talk and giving such a clear explanation of these tools and their capabilities.
Thank you so much.